Hello guys, nice to see you. Good afternoon. Okay, so during our last discussion, we introduced the concept of linear momentum and conservation of linear momentum for a closed system or quasi-closed system when external forces do not act or they are compensated. And also consider different types of possible collisions, like elastic, non-elastic, and ideally like perfectly non-elastic. So today we will continue our consideration of collisions. I guess we will start with collisions in two-dimensional space. So to highlight how this type of cases should be considered. And then we'll see how much time we have. We will introduce the concept of center of mass and discuss in details basic features of this concept. Okay, I think that majority of people who are interested have joined, and now probably I can switch to the slides where we can write and discuss things. So let us consider two-dimensional case x, y. And in this case, we need to deal with projections of linear momentum vector. And also if it's, for instance, elastic collision, we also need to take into account conservation of kinetic energy. So let us assume that we have such a case. We have M1 moving with some velocity V. Let's call it V1. And then it hits stationary M2. So it doesn't move. So V2 is equal to 0. So after collision, we need to consider which velocities will have both bodies and at which how it will be related to the angle of their velocity vector orientation. So after collision, we will have something like this. Let's show it here. Maybe let's make this axis a bit longer. So it will be axis x. And we will have something like this. It will be our body M1 with velocity vector v1, let's call it prime. So it's prime means velocity after collision. And here will be some angle theta. Then here will be body M with mass M2. This will be the orientation of its velocity vector. It will be v2 prime vector. And here will be some other angle. Let's call it phi. So in order to approach this, we need to consider that we have conservation of linear momentum vector, and that is true for projections of these linear momentum vectors on different axes. So initially we can write that M1 this M1 times V1 x plus M2 times V2 x is equal to M1 V1 x prime. So it's velocity after collision, like speed along axis x after collision, plus M2 V2 x prime. It's the same we can write for axis y. Let's do it. M1 V1 y plus M2 V2 y. And this is equal to M1 V1 y prime and plus M2 V2 y prime. So this is the general case when we split both initial and final linear momentum vectors in two components projected on axis x and y. Now let us see what do we have in this particular case. So initially we have M1 times V1 in the left of the first equation because our velocity, initial velocity vector is aligned along axis x. So it's moving horizontally. So full length of the initial linear momentum of first body is projected on axis x. So it will be M1 times V1. Then we have second component here, which is initial velocity of body M2 along axis x, and that is 0 because it doesn't move in any direction. So we have nothing there. So let's put it here, it equals 0, and here it's equals 0. And in this case, it's also equals 0 because we don't have any component of initial velocity v1 along axis y. So then we have two components in the right side. It will be M1 times V1 prime. So we need projection on axis x, and that will be times cosinus theta. So next, this is what we wrote stands for body M1. Now we need contribution from body M2. So it will be M2 times V2 prime and times cosine phi. Okay, so this is for axis X. Now for axis Y, we can write the following. So here we see both terms in the left side are equal to 0. So we can write 0 is equal to first our body M1. So it will be M1 times V1 prime. And we consider this component, which is projection on axis Y. So we need to multiply it by angle by sinus theta. Now we have component which comes from the second body, M2. And here we need to take into account that this projection is pointed downwards. So we have, it means in the opposite direction of axis Y. So this will come with minus here. Minus M2 times V2 prime times sinus P. So we already have two equations, set of two equations. And if only two parameters like angles, theta and phi, or initial and final velocity of body M1 are unknown, we already can calculate them based on solving this system of two equations, because system of two equations provide us with opportunity to get two unknown. However, if this collision is considered to be elastic, then we can also write equation which stands for conservation of kinetic energy, and that will be additional equation in this set of equations. So it will be mv1 squared divided by 2 is equal to m1 v1 prime square divided by 2 plus m2 v2 prime square divided by 2. So this will be kind of additional equation. So we can get already 3 unknown parameters from this set of 3 equations, linear equations. Okay, so this is the general approach, how you deal with elastic, for instance, elastic collisions in two-dimensional space. And let us consider some example. For instance, we have some cross, like T-shaped cross, two streets. So two cars are moving towards this cross. M1, V1. And here we have M2 and V2. They are moving perpendicularly to each other. At some point, they crash in the middle of this T-shaped cross. And this crashing point we will consider as our reference point for the frame of reference of our system of coordinates X and Y. Then we have inelastic, let's assume inelastic collision between these cars. they kind of stick to each other and are moving in as one body with some velocity v at some angle theta to the axis x. So let us see what we how we can get some information about the conditions after these perfectly inelastic collisions, a collision of two cars. So first, let us consider components along axis x. So along axis x, we have, since this is inelastic collision, we cannot deal with conservation of kinetic energy, because as we know, part of kinetic energy is converted into internal energy, and obviously we cannot have this conservation of initial kinetic energy. So it will be not applicable, this concept, for inelastic collisions. So we deal with conservation of linear momentum. So initially we have m1 times v1, because this one is aligned in parallel to axis x and in the same direction as axis x. So it stays with sign plus. Then it is equal to the linear momentum vector projection on axis x of these two cars attached to each other after collision. So it will be m1 plus m2. And then we need to find the projection of the velocity vector on axis x. Will be v times cosinus theta. So this is true for axis x. Now, any ideas how it looks for axis y? One, two.
Can I ask, please?
Yeah, sure.
If I'm not mistaken, in the book, there is no cosinus theta in x-axis. Your first question, why the cosinus theta?
Because we are talking about projection of our final linear momentum vector on axis x. And here is our vector v, velocity vector, and we need to consider x component of this. So it will be, here is some angle theta. So we
just replace cosine with
projection on axis x. Now we will do this as projection on axis y, and that will give us a set of two equations.
m1 plus m2 be sine theta, perhaps?
That will be for axis y, what we are going to write next.
Yeah, that's you asked before if we had any way to find y.
Yeah, that's true. So we can write, now we have m2 times v2, because we see that this vector is aligned along axis y. It will be m2 times v2. And this is equal projection of m1 times v1 is equal to 0 on axis y. Here we have the sum of two masses, m1 plus m2, and v times sinus, as you mentioned, theta. Okay, now we have this set of two equations, which describes this perfectly inelastic collision of two cars in two-dimensional space. And what can we get out of it? So we can divide one equation, first equation, let's say maybe better second equation by first equation. So if we divide second equation by first equation, we will get such a ratio. It will be M2 times V2 divided by M1 times V1. Then we will cancel out these parts. They are the same here. V times the parenthesis with the sum of two masses, and there will be sinus theta divided by cosinus theta, and that is tangent theta. So we can already define the angle at which these two cars after collision will move, and that is defined by the ratio of initial linear momentums of the first body and the second body, I mean first and second cars. So if we, for instance, have some linear momentum of second body much larger than linear momentum of the second body, we see that it will be dominant for the direction of the motion after the collision. And if in the opposite, M1 times V1 is much larger and it's in denominator, so it will, this ratio will tend to 0, and tangent theta will be approaching 0. So it will be kind of sliding almost in parallel to axis x. Also, another parameter which is relevant is the velocity v, which we can get from this equation. And in this case, since we already know theta, we can substitute it in, for instance, first equation and express this velocity m1 times v1 divided by m1 plus m2 times cosinus theta. So this is an example of considering some case of perfectly inelastic collision in two-dimensional space. Before we proceed further with the center of mass, I would probably like to show you one interesting example. Let me try to share my screen. 1 second. Okay, do you see my screen now?
Yes.
Yeah, so we see such a kind of quite common toy when we have 5 metal balls attached to some very thin ropes, and you can deflect one of these balls. And what we see here, once it hits back to this stack of balls, then linear momentum is transferred to the final ball from the other side. So it is moving with the same velocity. So they have equal masses, and it kind of continues for going back and forth for several times until it stops because of some friction. However, the situation which never happens. So if you hit with one ball, never happens that two balls are deflected. And technically, it actually should be possible from first point of view, because if you consider you just need, in order to satisfy this requirement for linear momentum conservation, since masses are the same, then if you have twice larger mass, you just need to have twice smaller velocity, and that's fine. You can write that m times v is equal to 2m times v divided by 2, and that is true. However, it never happens. And any ideas what is the reason for that? Which type of collision is this? So these balls are very hard and they don't.
Perfectly elastic. Elastic.
Yeah, so this is elastic. And we already discussed that if we have elastic collision, then not only conservation of linear momentum is valid, but also conservation of kinetic energy.
Kinetic energy is the same, yes.
Yeah, it should also be the same, because we neglect with any deformation of these stainless steel balls. In this case, both conservation of linear momentum and kinetic energy should be applied. And you can see, if you proceed further with this not possible scenario, that if we have m times v squared divided by 2, and then consider that we have two masses, it will be 2m times v divided by 2 squared. So in the divided by 2. So in the denominator, eventually we will get mv squared divided by 4. So obviously mv squared divided by 2 from the left side will not be equal to mv squared divided by 4. So that violates the requirement for conservation of kinetic energy, and that's why it is impossible. The only way how you can manage to have two balls deflecting after collision, you need to pull away two balls. Then if they hit these three balls, then two will go to the opposite direction. And then we will have conservation of both energy, kinetic energy, and linear momentum. However, if you use only, like play only with one, then this scenario when two will deflect after collision is impossible, because conservation of kinetic energy is violated. So that's why it will be only like this situation. So this is another example of elastic collision, when we need to take into account both conservation of linear momentum and kinetic energy. Okay, let me stop sharing this screen. And now I believe we can proceed with the introduction of the concept of center of mass and why it can be explanation, discussion, why it's relevant and could be helpful in different situations. Okay, so it is defined that translational motion of a body can be described by a mathematical point, which is located within this, let's say, three-dimensional arbitrary shape body, which like if all mass of this arbitrary shaped body is concentrated in this single point. So this single point is called, in this case, a center of mass, the center of mass for this body. And that is true for translational motion, because then later we will discuss in details rotational motion. But now this is what we are talking about. That's relevant for translational motion. So let us consider probably the most simple case. Will be two masses along axis X. So it will be mass M1, mass M2. And from origin, so this is coordinate of like X1, position of the center of this mass. And here we have coordinate X2. So the task is to calculate the center, position of the center of mass. And in this case, the approach for calculating this position, X center of mass, we will call it, will be equal to the sum of products of coordinates of like mass of the first body and its coordinate x1, so it will be m1 times x1 plus mass and coordinate of body number 2 will be m2 times x2, and then divided by the sum of these two masses, m1 plus m2. So this is the approach for this particular case. Center of mass will be determined by the masses of these two bodies and their location. So let's say if M2 is larger than M1, let's say M2 is larger than M1, obviously that this center of mass, coordinate X center of mass, will be closer located to second body than to the first body, because more mass of the system within this within this configuration will result in center mass closer to the heavier body. So if we have a system of many bodies, then the average, so this calculation of the center of mass along axis X can be calculated as follows. So we have X center mass, so it's in general case of many bodies. We have sum of all, for all bodies, products of mass of this body and its position along axis X, divided by the sum of all masses along this axis. And in this case, we can like sum of all masses of the object which forms the system which we consider. So in this case, we will have something like this. It will be 1 over capital M, which stands for this sum of all masses. So it will be M, capital M is like mass of all system, times this sum of products Mi times Xi. So that is valid for one-dimensional case for position along axis X. However, if we need to do it for multidimensional space, obviously, this center of mass will have its coordinates along different axes, y and z included. So in this case, we can write the same for axis y, center mass is equal to 1 over this mass of the system times the sum over all bodies mi times their position along axis y and position along axis z will be equal to 1 over m, capital M, times the sum of mi times zi. So this will give us coordinates for x, y, and z for the center of mass. And in other format, the position of the center of mass can be given by the position vector. So it will be r center of mass is equal to x center of mass times I unit vector plus y center of mass times j unit vector plus z center of mass times k unit vector. So that is the general, the most common and universal way to set the position of a point. And in this particular case, it's a special point, which is center of mass for the system of bodies. We give it with, define it with this position vector. And here are components of these position vectors along different 3 axes. So now what if we have not uniform distribution of, so let's say we have some continuous body. So so far we were considering a system of many bodies, but that is one case. But could be also case when we have some continuous body with uniform or not uniform density distribution. So in this case, we need to consider some limit, x, let's say for position of center of mass along axis x, xcm will be then equal to limit delta m approaches to 0. So we will consider very small, like tiny parts, like pieces of this continuous body with mass approaching to 0 of this equation, 1 over total mass of the continuous body, sum of delta mi times xi. So each of these small volume of the continuous body which we consider will have certain coordinate along axis x, and we will have a product of this small mass delta mi on its position. We'll do it for whole volume of this continuous body and sum it up. In other words, it will be integration. So be equal to 1 over total mass integral of x times dm. So we need to integrate all over this small parts of the continuous body, and that will give us the concentration, the position of the center of mass along the axis x. If we do it for the 3-dimensional case, then RCM, position vector, which defines the position of the center of mass for this continuous body will be 1 over m integral position vector dm. So for each this small element of the continuous body, there will be its position vector. If we integrate this for all volume, we will get the and divided by the total mass, we will get the position vector for the center of mass for this continuous body. Let us do some examples. For instance,
Excuse me, Professor, I have a question.
yes.
If you go to the previous slide, and then
Mhm.
there I have a question, like why at the first place you wrote like delta m limit goes to 0 and delta m at all, like why? Can you repeat, please?
Oh, so if we have, so this equation, which stands here, is that one which we got for a system of individual bodies. So it's not continuous bodies, it's some system of many bodies. And then we have very clear definition of what mass of this body is and what is position of this body. So we may have many bodies, but they are kind of separate. However, in case of a continuous body, let's say we have one body, but it's random, arbitrary shape and continuous body, then in order to calculate this position of the center of mass, we need arbitrarily divide this body in very small parts with the mass delta mi. Each of these part will have mass delta mi and will obviously possess some its position like coordinate because this is continuous body, so different parts of this body will have different position. In order to get the accurate calculation, we need to take as small volumes, as parts of this continuous body as possible. That's why we go with this limit delta m approaches to 0. And mathematically, that's nothing else as integration of x over dm, x times dm. So that is the approach which you need to go in order to calculate position of center of mass for a continuous body. Let's say here we consider a one-dimensional case, coordinate along axis x. So it could be some metal rod, and then we need to divide it in small parts with masses delta mi, use this limit that delta mi approaches to 0, so we have very small pieces, and that is integration along this rod in order to get the position of the center of mass, which we will do next. Is it clear?
Yes, thank you very much.
You're welcome, no problems. Okay, so now we have some time, probably we can do one example and another example with non-uniform distribution of mass we will consider on Friday already. So let us consider some rod with some linearly distributed mass lambda, which gives us, for instance, kilos per meter. So linear distribution, like linear density. So the length of this rod is L. And here we have axis X. So this is one-dimensional case. Then what we need to do, we as we discussed previously, divide this rod in small pieces, dx, with position x. And then we need to integrate over all rod. So position of this center of mass will be equal, we know already that equation, it's 1 over total mass integral of x times dm. Okay, now we need to think what is dm. dm, how we can express dm of this in this particular case? Any ideas?
dx lambda.
Good, yeah, it's lambda times dx, because lambda is our linear density. So if we multiply it by the length of this small element, it will give us the mass of this small element. So that is convenient now because we can go from dm to dx, and that is what we need to do. 1 over m integral x, instead of dm we put lambda times dx, lambda dx. So this lambda is a constant, so we assume that this is uniform rod. Next time we will consider case when it's not uniformly distributed. So we can take it out from integral lambda over m integral x dx, and we need to set the range, like the limits for integration. So it goes from 0 to L, like total length of the rod. And this will be equal to lambda over m times x square divided by 2 from 0 to L. Now, if we substitute these limits, we get lambda times L square divided by 2m. Okay, now we need to also express m, like this capital M, total mass. So total mass of the rod will be this lambda times L, total length of the rod. And now we can substitute it instead of this total mass. So here it will be lambda L square divided by 2 lambda L. And we eventually, so we cancel out this lambda L n square. It will be L divided by 2. Kind of trivial result, because we see that this center of mass, x sm, is located right at the middle of this rod, which makes sense because this rod is symmetric and the mass is distributed, this linear density is constant, so mass is distributed uniformly. However, with this accurate approach for calculating the position of center of mass, we got this result, L divided by 2. Next example, which we will consider on Friday, will be in the case when lambda is not constant and it depends on x. So obviously that will change the situation, will make it a bit more interesting. Okay, this is everything what I wanted to tell you for today. So we introduced initially discussed some examples of collisions in two-dimensional space and introduced the concept of center of mass. have shown how it can be calculated for the system of many bodies, and also considered the case of a continuous body with arbitrary shape, how it will be possible to calculate center of mass for such a continuous body. So we will continue next discussion with the example of this not uniform distribution of linear density case, and proceed further with other possible applications of conservation of linear momentum. Okay, thank you very much for attention, and hope to see you on Friday.
Thank you. Goodbye.
Goodbye. Thank you.
Take care.
Goodbye. Thank you. Goodbye.
Bye-bye.
Thank you. Bye.